Number one, the equation AX equals 0 always has at least one solution. True or false? True. What is the one solution it always has? The trivial solution, which is the 0 vector, right? Everything is 0. So this is true. Okay. True or false? An equation with no solutions is called trivial. False. An equation with no solutions is called inconsistent. And trivial represents, what was the word trivial for? The 0 vector as a solution. Yeah. So this is just, I just put in a bunch of words and made a nonsense sentence. If the equation AX equals 0 has one free variable, the solution set is a what through the origin? A line. Yeah. Non-trivial, it's a non-trivial through the origin? No, it doesn't make any sense. Okay, so this first page of their notes that I just gave you are just my notes on the reading, right? So I tried to like take the reading and condense it into a page, give you an example of what the notes should be. And as I was trying to write the lesson, I took notes. I just tried to do I happened to do my own notes, and I said, wow, these are really helpful. I think I'll give them to the class. So you can read through those sometime on your own. I won't read them to you. Today we're going to talk about section 1.5. Today's actually class number 7, if you like to keep track of these things, because last class was 6, the quiz. So today we're going to learn how to express the general solution to a linear system, which we already know how to find, right? We're just going to learn how to express it in a new notation, more new notation, parametric vector form. We're also going to look at the relationship between the solutions to a homogeneous system and the solutions to its associated non-homogeneous system and its associated homogeneous system. And then finally, we're going to practice describing solution sets of linear systems geometrically. So the reading, it basically is broken into 2 really big topics: how to write something in parametric vector form, and how to describe a solution set geometrically. So I kind of summarized both of those things, and then now we're going to practice doing them. Okay, so on the individual part of quiz 1, you solved this system. So this is 3 equations, 4 unknowns. Let's write out a matrix equation for the associated homogeneous system. Matrix equation. So I'm going to write out the coefficient matrix, which is 1, 0, 2 for the x1s, and then the x2 coefficients are 4, 0, 8. My x3 coefficients are -2, 3, -4. My x4 coefficients are -3, -3, -6. And then I have a vector of unknowns. How many x's do I have to put in there? 4, because I have 4 unknowns. x1, x2, x3, x4. So this is my matrix A, the coefficient matrix. This is the vector x, the vector of unknowns, and that has to equal the answers to the equation. Whoops, sorry. But I'm writing the associated homogeneous equation. And what's a homogeneous system? What's the definition of homogeneous? AX equals 0, right? So instead of 6, 0, 12 is the other side of my equations, right? I'm the associated homogeneous equation is just when I replace those guys with zeros. So we're solving AX equals 0 instead of AX equals 6, 0, 12. How do you solve this thing? Make an augmented matrix and row reduce it. So we're not going to do that because I know you know how. So I'm just going to tell you that that's what you do. Set up an augmented matrix and row reduce it to find the solutions. And to save us a little bit of time, here are the solutions. Okay. Hopefully, you came up with something that looks like this on the quiz, but this is the homogeneous system, not the exact system you solved. X3 equals X4, yeah. Because you have to write X3 in terms of the free variable X4.
Right. You also have to.
Yeah, you write X4 is free. So you have two free variables, and your other two variables you write in terms of the frees.
So I had the option.
Yeah. Okay, so here's our solution system, our solution to the system. So I want to write this general solution in parametric vector form. So this is the new thing that we're going to do this class. So any solution, like you could pick some numbers for the free variables and get an x1 and an x3 so that you'd have a specific solution rather than the general solution. And any solution can be written as a vector, right? X1, X2, X3, X4. Right? So here are my unknowns. We now know that this equals -4x2 plus 5x4. x2 is free, so I'll put an x2 here. x3 is x4, and then x4 is free. So this is what any typical vector looks like. You would pick a value for x2 and x4, and then figure out the other two values. No, you would write it. So what you wanted to do on the quiz was that's exactly what you should have written. We're learning a new notation now. Yep. So if something's a free variable, you just write it. You just write, if x4 is free, you just put in x4. Okay, now I'm going to break this thing down into a linear combination of vectors. So I'm going to do something, my only free variables are x2 and x4. So I'm going to do some vector times x2 plus another vector times x4. So I just want to like sort of pull the free variables out. So what should go in this column vector? -4, 1, 0, 0. So I'll have -4x2, x2, 0, and 0. So I've got all my x2 terms accounted for. And then what should go in this column vector so that I have all the x4s I need? 5, 0, 1, 1. And then when you combine these, we're going to have -4x2 plus 5x4, right? When you add them together, you'll get this vector. So this thing I just wrote here, this is called the parametric vector form of the general solution. There's like a 4-step process written in your text about how to do this. I have it written right here. Right. Row reduce the augmented matrix to reduced echelon form. You did that on your quiz, or we pretended we did that. Express each basic variable in terms of any free variables. Write a typical solution x as a vector whose entries depend on the free variables. And then decompose x into a linear combination of vectors where the vectors only have numbers in them and the free variables are the weights. So that's exactly what we've done here. I wrote a typical solution vector x using the free variables in terms of the free variables, and then decomposed it into a linear combination where my free variables were the weights. All right, so let's take each of the free variables to be 1 and just check that that's a particular solution to the homogeneous system. So what happens if I make x2 and x4 1? What vector do I have? One, 1, 1, 1, right? If x2 is 1, my first entry is going to be -4 plus 5, and then I have 1 plus 0, 0 plus 1, and 0 plus 1. Why? Oh, so if this x2 were a 1, right? When you multiply a whole vector by a scalar, you just multiply every entry. So if this were a 1, that vector just becomes -4, 1, 0, 0. If x4 is a 1, this vector becomes 5, 0, 1, 1. And then you add the terms. -4 and 5 makes 1, 1 and 0 makes 1, 0 and 1 makes 1, and 0 and 1 makes 1. That makes sense? So if I pick some weights, because these two variables are free, I can make them anything I want. So I just picked an easy one, 1, and I got, this is one particular solution to my homogeneous system. So my general, there are infinite solutions, because I can put in any numbers for x2 and x4 I want. This is one particular solution, and I want to check that it's a particular solution. So that means I need to check that my coefficient matrix, 1, 0, 2, 4, 0, 8, -2, 3, -4. There's my coefficient matrix. If I multiply that by my unknown matrix was x1, x2, x3, x4, this is one set of solutions to that. So if I put in 1, 1, 1, 1, do I get 0, 0, 0? Right? This is how we check. You take the solution, you plug it in, you say, is this equation true? I use that all the time for checking. Does it equal? Yeah. So what do you think? Does it equal it? I guess I should have given myself a little more room to write it out. So remember, you pick up the first whole row, turn it 90 degrees, lay it on top of the vector. The entries that match up, you multiply, and then you add it all together. So I have 3 rows, so I'm going to have to do that 3 times. So my resulting vector is going to have 3 entries. So I'm going to have 1 times 1 plus 4 times 1 plus -2 times 1 plus -3 times 1. My first entry of my resulting vector. So that's my first row times the column 1, 1, 1, 1. Then I take my second row and multiply by the column 1, 1, 1, 1. And I have 0 times 1 plus 0 times 1 plus 3 times 1 plus -3 times 1. Third row times the column 2 times 1 plus 8 times 1 plus -4 times 1 plus -6 times 1. So this is 1 plus 4 is 5, minus 2 minus 3 is 0. 0 plus 0 plus 3 minus 3, 0. 2 plus 8 is 10, minus 4 is 6, minus 6 is 0. So it is a solution. So this doesn't prove that our general solution is definitely correct, but it's like really good evidence, right? If you get a general solution, pick one particular solution, check it, and that's good evidence that your general solution is correct. So this turns out to be equal. All right, so I want to describe the solutions of this homogeneous system geometrically. So this is my general solution right here. Geometrically, what is that thing describing? It's a plane through the origin. Yeah. So we have 2 free variables. So the thing it's describing is going to be 2-dimensional, a plane, right? 2 free variables, so we're going to have a plane. And you can think of these as points, -4, 1, 0, 0, and 5, 0, 1, 1. So we're taking a linear combination of those 2 points and also the origin. Okay. So 3 points determine a plane. So if you just lengthen these as vectors, right, by multiplying by scalars, and you can add them together, so you're like spanning a whole plane. So those, think of these 2 things as lines, right? 5, 0, 1, 1 is a point in 4 space. Can't really picture 4 space, but it's a point in 4 space. here, and when you multiply that by a scalar, you're just like stretching or shrinking that vector. This is also like a line, because this is a vector in 4 space. You multiply by a scalar, you stretch and shrink it, and when any two lines determines a unique plane. Okay, so this thing is a plane in R4, which we can't picture, but it's a plane in R4 that passes through this point and the origin. And my vectors were 4, 1, 0, 0. 5, 0, 1, 1. What's the question, Iris? Yep, because that was the original equation from number 1. How do you get it to equal that? You have to multiply each row of this matrix, the coefficient matrix, by the vector 1, 1, 1, 1. And nope, it gives you 0, 0, 0. Because the way you multiply matrices by vectors, yeah, add it all up. That's it for the demo. You're going to work through, the next thing you're going to do is you're going to work through basically these same questions, but for the non-homogeneous system that you did on the quiz.